So we're going to take a look at some equivalency of statements here. So when we talk about real zeros of polynomial functions, if f is a polynomial function and a is a real number, the following statements are equivalent. Okay, so statement 1, x equals a is a zero of the function. Statement number 2, x equals a is a solution of the polynomial equation f of x equals 0. X minus a is a factor of the polynomial f, and the point a comma 0 is an x-intercept of the graph of f. So this is, all of these statements are equivalent. So anytime that we set f of x equal to 0 and then we solve for a, we're finding the solution, we're finding the 0. We know that x minus a is a factor. We know that those solutions or those zeros that we find are actually the x-intercepts of our graph. So let's take a look here at finding the zeros of a polynomial function. So here what we need to do in this particular case would be to begin by factoring. Okay, so we can factor this out. So f of x, and we'll factor out a negative 2x squared. And then inside this will factor as x squared minus 1. And then note again, we can factor the x squared minus 1 because it is a difference of squares. So it will factor as x plus 1 and x minus 1. By setting each of these equal to 0, so letting f of x be 0, we know that we can determine our solutions. So we'll first look at what is going to make our factors be 0. So here in this x plus 1, if I substituted a negative 1 in for x, that would get me a 0. If I substituted in 1 for x minus 1, that would also be a 0. And the only way to have negative 2x squared be 0 is if x is 0. So we know that our zeros are these points. Okay, so the real zeros are at x equals 0, x equals negative 1, and x equals 1. And that means that our corresponding x-intercepts are then 0, 0, negative 1, 0, and positive 1, 0. Okay. Sometimes we get zeros that are repeated, so they happen a few times. And you'll see that I wrote some notes here about those as well. So a factor x minus a to the k power, where k is greater than 1, yields what we call a repeated 0. Okay, so this is a repeated 0, exponent a of multiplicity k. So when we have a repeated 0, it means that that 0 happens a few times, and the number of times that it happens is indicated to us with our multiplicity, which is that exponent. So if k is odd, the graph is going to cross the axis at x equals a. And if k is even, the graph touches the x-axis but does not cross it. So think a lot of times that means you have a vertex of a parabola, for instance, that's sitting on the x-axis. So it's touching it, but it doesn't cross it. So here we're going to take a look at sketching the graph of f of x equals 3x to the fourth minus 4x cubed. And we're going to do this without using a graphing utility. So no Desmos, no graphing calculator, nothing like that. Okay, so we're just going to check this out here. So we're going to describe the end behavior of the graph. So in order to do that, we know that our degree is even, okay, because it's 4, and our leading coefficient is 3, which is greater than 0. Okay, so in this particular case, our end behavior is going to be increasing in both directions. So what this means is as x approaches negative infinity, f of x is approaching positive infinity, and as x is approaching positive infinity, f of x approaches positive infinity. And then it's asking us to write the zeros of the polynomial. Okay, so we can factor this. F of x equals 3x to the fourth minus 4x cubed. I can factor from this an x cubed. So I'm left with 3x minus 4. So the only way for our x cubed to be 0 is if x is 0. And then we can set 3x minus 4 equal to 0, and we can solve this. So 3x equals positive 4, divide by 3. This is giving us x equals 4/3. And you want to leave this as a simplified improper fraction. So you wouldn't want to give me something like 8/6, but 4/3 is a perfect thing to go with there. Okay, so both of these, we can talk about the multiplicity of these. So they're both odd, so we're going to cross the axis at both of those points. So we're not going to bounce off of those, we're actually going to go through the axis then. So and those points that we have are 0, 0, and 4/3, 0. So we actually have a lot of information about our graph at this point. So we're going to plot a few additional points. So we don't want to use anything as far as things that we've already used. So we don't want to use our intercepts here. So let's take a look here at what if we used -1 and 1. Let's just plot these two. So with -1, if I substitute this in, we'll have 3 times -1 to the fourth power minus 4 times -1 to the third power. Now, -1 to the fourth power is 1. 3 times 1 is 3. -1 to the third power is -1 times the -4 is going to give us a positive 4. So this is 3 plus 4, which is, whoops, 7. And then if we substitute in a 1, we will have 3 times 1 to the fourth power minus 4 times 1 to the third power. Obviously 1 to any power is 1, so this will be 3 minus 4, which is -1. So we have a few more points here, and those points would be -1, 7, and 1, -1. So we can sketch a graph then of our function. So we know we have a point at 1, -1, So we'll plot that there, 1, -1. And we know we also have a point at -1, 7. And remember, this is just going to be a rough sketch here. At 4/3, so that's a little bit above that, right there. We'll cross the x-axis, and we also cross the x-axis here. And we know that we have our end behavior. So we know that we are increasing without bound in either direction. So this is going to look something like, oops. Something along the lines of a very thin parabola.